Hey everyone, welcome to our final video lecture of the entire semester of ENES 102. Today we're going to be talking about friction. Now I'm sure you're all very sad that this is going to be the last set of video lectures that you get, and I can imagine you all are probably feeling quite a bit like this character over here. Right over here. You don't want to leave, you want to stay, you want to watch videos forever. Unfortunately, you've got other things that you should go off and do in your life, and I should probably stop making terrible jokes, and I'm going to try and push you this way. Now, with friction, we all know that friction and you, no matter how much I try, you're going to try and fight back and prevent yourself from moving via the force of friction because you want more jokes and more baked goods and potentially more free money. Well, none of those things are coming, at least not today. So let's get on with it and start the rest of our lecture on friction. Okay. To describe friction, friction is the force resisting the relative motion of solid surfaces, fluid layers, and material elements sliding against each other. Now, we've worked with friction throughout the semester in a couple of different ways, and I'm sure you've all seen and experienced it yourself. But really, I like to kind of highlight friction in an interesting and very bad joke kind of a way. When you look at the force of friction equation, it actually looks like a word that some of you are probably pretty familiar with. F-U-N. Fun. Now hopefully you've all had a fun time in ENES 102 this semester. And to finish things off with one of the worst jokes I ever tell, I'm going to sing you all a little bit of a song. Now, how many of you growing up were SpongeBob fans? Who remembers the fun song? Now, I would sing you the fun song, but that's copyright infringement if I did that, and I don't want to get sued by SpongeBob. He might seem really nice, but he actually has a dark side. Now, what I've done for you is I've kind of adapted the fun song to the friction song. So let's explain what the friction song is. Whew! Alright, here we go. F is for friction, acts on all objects. Mu is for the coefficient of friction. N is for normal force, and any time at all here on the planet Earth. Okay, I apologize for that terrible singing, but this is going to be relevant in a little while. Friction is fun. It's mu times n, which is the coefficient of friction times the normal force. Now, hopefully, you all benefit from me embarrassing myself, and you remember that for the rest of your lives. Now, there's two types of friction. There's static friction and there's kinetic friction. We know that static friction is going to be a higher value than kinetic friction, and the reason is because when two solid surfaces rest against one another for a very long time, they become enmeshed in a way, and it takes more force to get things moving relative to each other because those bonds have to be broken. Kinetic friction looks like some weird funky teeth where the bonds are already broken, so one thing can slide on top of the other relatively easily. That's why we see this relationship here, that static friction is always greater than kinetic friction. Now, what type of friction do you think we'll use in this class? Well, hopefully you're not a dummy, and you realize static friction is going to be the type of friction we use in this class because the word static is there. So, now that we know the equation for friction, let's solve a very simple problem. I want you to look at this problem right here. What we've got going on is we've got a box. We're applying a force of 30 newtons to it. We've got all our coefficients of friction over here. We've got gravity. And our question is, what is the force of friction? Okay, why don't I give you a little bit to solve that and think on it. All right. I'm sure you've all got giant brains and you figured it out just like I did. So let me show you the steps. We know that the force of friction is mu s times n. Friction's fun. Okay. So we know mu s, that's 0.5, and we know n, that's just the normal force, which if we did a sum of the forces in the y, would be the weight, the mass times g. So, force of friction is 0.5 times 10, which is 50 newtons. So, there we go. Force of friction in this particular problem will be 50 newtons. Hell yeah, we're freaking awesome. Let's give ourselves a gold star. Now, wait a minute though. If this were true, let's think of another example real fast. If we have here, in this problem, we apply a 30 Newton force to this 1 million kilogram block, and we'd use the exact same equations and setup that we did in the last problem, we would find that the force of friction would be freaking huge. It would be a value of 5 million newtons. If this were true, we would all be really, really screwed, because we would pretty much have to tiptoe through life. Otherwise, anytime we touched any heavy object to lean on it or push it, friction would push back with nearly infinite amount of force. And you could imagine that if you tried to push a building or a mountain, the amount of force that would be acting on you would probably be enough to cause you to explode or turn to dust immediately. So the good news is that we were actually wrong in the first slides we just showed. There's another way to calculate friction. We have to realize that the force we calculated previously, mu s times n, is the force of friction maximum. So that's going to be the maximum force that friction can provide. Well, how do we solve for the force of friction acting in this problem? Well, we do some statics. And we do that the sum of the forces in the x equals 0, which will tell us that the 30 newtons to the right minus the force of friction has to balance out if this box is going to remain in equilibrium. So what we find is that the force of friction is 30 newtons. Now, this is exactly why I said before that force of friction is fun. Friction wants to do the absolute bare minimum that it can do, just like all of us, especially when we have homework to do. We don't want to do homework. We want to go out and we want to have fun, whatever that means for us. So if friction can provide a maximum force of 50, it's only going to do that if it really needs to. So in this case, when we apply 30 newtons, friction only pushes back with 30 newtons. It goes out and it uses its other 20 newtons to go and do TikTok videos, or Snapchat, or Facebook, or something else. I'm dating myself and probably sound super old and lame, so let's move on. If we push on our block with 50 newtons, what would happen? Well, now friction would be a little bit less happy. And the reason why is because, oh no, it has to provide its maximum amount. It can't even put any amount of energy towards going to have fun. So friction's pretty sad right now. What would happen if we applied 51 newtons? Uh-oh. What would happen is that the force of friction for a very brief moment would be 50 newtons, the static maximum friction. But after static friction is exceeded, we would achieve a value of kinetic friction, which is 10 newtons. So that's a good overview of kind of how friction works and the difference between static and kinetic frictions. Now let's look at this problem here, which is actually very simple and basic, but it's to illustrate kind of what we're going to be doing with the rest of the friction problems we approach in this class. So in this problem, we're told that the coefficient of friction between the two blocks is 0.4. And we're told that the weight of block A is 10 pounds and the weight of block B is 7 pounds. If we apply force on block A, how much force would we need to apply to move block A? Well, this is a very common question here in ENES 102. Essentially, what we're going to be doing, if any time we're talking about moving a block or moving a system of blocks, what we need to do is we must exceed the force of friction maximum. So in this particular problem, what we can see is going to happen is that we have a frictionless floor down here, so there's no friction, and we have friction between the block and block A. So essentially, if we drew a free body diagram of our top block, there's going to be a tension moving this way, a normal force going this way, a weight going down this way, and a force of friction. Now, if the rope had been cut that rope, and we pulled on A, block A would move with block A. So what we can see is that the force of friction actually wants to pull block B with block A. So that would be our force of friction. So, if we look at block A, pretty much the only thing that's touching it, and that is affecting block A, is going to be this applied force, this force of friction from the top block, and this weight. Now, the force of friction in the top block, remember, is fun. So, this force of friction is going to require two things, and that's why I'll circle it in blue. And the two things that are going to be in that force of friction equation are 0.4 and N. And we can see that N is really just W. So to solve this problem, the sum of the forces in the X on block A is equal to 0 will equal to F applied minus mu S times NB. So F applied in this case is 0.4 times 7, which tells us that the force needed to move block A has to be equal to the maximum force of friction that block B can apply to block A, which in this case is 2.8 pounds. Now, had we had friction down here, that would have been added into your problem over on this side, and this value would have gone up. But we kept it very simple because our next question gets quite a bit more complicated, but although it looks pretty tricky, it's actually not that challenging, and I'll show you how to do that in a hand solution in just a second.
All right, everybody, let's solve our first friction problem, which is involving this tractor and this big old heavy log. What we're told is our tractor is called a front end loader and that it weighs 8,000 pounds, which actually makes sense because a typical Chevy Suburban SUV weighs about 7,000 pounds. So this actually is a little bit heavier than that, which kind of makes sense. And we've got that its center of gravity is shown at this location G right here. We're told that the coefficient of static friction between the log and the ground is 0.5 and between the rear wheels of the loader and the ground is 0.8. So it's going to be key to remember here that we've got two different coefficients of friction. So for the wheels, we have a coefficient of friction of 0.8, and for our log, we have a coefficient of friction of 0.5. Very common mistake that people make in these problems is they just get a little mixed up and they switch the coefficients of friction. So now what we have to do is look at this assumption that we're making right here. We're told that the front wheels are free to roll, and we can assume that the engine does develop enough torque so as to cause the rear wheels to slip. Okay? So what this basically means is that only our back wheels are powered wheels. Our front wheels are just there to roll, very much like a bicycle. So this is basically what we're told, is that the front wheels just kind of are there. They're there to add control and balance, but otherwise they're not actually doing any work or applying any force to the ground. Only the back wheels apply tractive force. And if you've taken ENES 100, this is actually probably something you've talked about, and you'd realize that this is referring to a 4x2 vehicle, a vehicle with four wheels where only two are powered. Our question that we're asked to solve is to determine if the front loader can push the 550 pound log up the incline. So our question is, can this giant truck over here push this log up the hill? So essentially, that's kind of like a two-part question. We have to figure out how much force it takes to move the log up the hill, but we also need to find out how much force it takes the front loader to move up the hill. And pretty much that's what we're going to do. So we're going to answer this first question here, which is how much force to move the log is required. Okay, so what we're going to do is draw a free body diagram of our log first. So our free body diagram of the log is a classic box on a ramp problem, pretty much. We've got a long rectangular box. We know that we've got our hill, and we're told that our hill is inclined at 10 degrees. Next thing that we want to do is we want to draw the weight of our log. And because it's a rectangle, we know that the weight is going to act straight down. I like to draw the weight very long and down. That way it's easier to draw our components. So we're going to have two components. We're going to have W cosine 10 degrees. And we're going to have W sine 10 degrees. So we've got a weight going into the ramp and a weight going down the ramp. Next, we're going to have our normal force acting on the log this way. Something we can see is that the front loader over here is applying a force. So we'll call this F of the truck on the log, FTL. And what we're told is that is 1.25 feet from the ground. Now, we're obviously in the friction chapter, so we're going to have a frictional force in here somewhere. Because the tractor is trying to push the log up the hill, we know that we are going to have a frictional force pushing down the hill. And that's going to be directed at the bottom right corner. Now, I've drawn it in blue so that we can keep it straight with our 0.5 frictional coefficient at the top. Okay? Now that's it. That's all that we have acting on our log. So we need to figure out kind of this balance of x forces. So when we go to sum the forces in the x direction here, we'll set that equal to 0. That's going to tell us that the force of the tractor log minus the force of friction are going to cancel out. But we're also going to have minus weight sine theta, or weight of sine 10 degrees. Now for this problem, which I didn't stipulate a second ago, but it should be pretty clear, is that I'm going to line up my axes in such a way such that the x-axis lines up with the hill and the y-axis is perpendicular. This will allow me to kind of do everything simpler because I already can see the new y and x components of my weight. So this is my equation right here. F of the tractor on the log, I don't know. The force of friction, that's what I'm trying to figure out. And the weight sine theta, I actually do know that because pretty much I was given two things in this problem to work with, which was the front end loader's weight of 8,000 pounds and the 550 pounds of the log. Okay, so what are we going to do next? We've got the sum of the forces in the x. I've got two unknowns, so that's not going to work out. I need to write a sum of the forces in the y equation. So when I write a sum of the forces in the y equation, I set that equal to 0. Let's look at what forces I have in the y. Well, in the y direction, I've got the normal force going up, and I've got minus W cosine of 10 degrees. So what this tells me is that my normal force is equal to 550 pounds times the cosine of 10. Okay, so I know that in order to push this log up the hill, I'll have to exceed maximum friction, which is the mu static times n, must be exceeded to move the log up the hill. Right? So if that's the case, then essentially I'm going to solve for FTL, which is the force of the tractor on the log, in order to push it up the hill, must be equal to mu s times n plus W sine of 10 degrees. So essentially, this is going to get us a value of 0.5 times our normal force, which was 550 cosine 10, plus the weight of the log, which is 550 sine of 10. Sorry, I ran in a room a little bit right there. But from this right here, what I can solve is that FTL, or the force of the tractor on the log required to push it up the hill, is equal to 366.3 pounds. Okay, so that's what we've got here. That the force of the tractor to push the log up the hill is going to be 366.3 pounds, and I've included a little note here so you can remember that when you go back to look at the notes on paper. The next question is going to be, now that we've looked at the log, we need to draw a free body diagram and look at our tractor. Now, rather than draw a free body diagram of this on my own, I'm just going to draw everything on this picture here. Actually, you know what? That would mean I'm too afraid to try and draw this tractor, which I bet you I can draw this. I'm going to pause the video while I draw an awesome tractor and then come back and solve the rest of the problem. Oh yeah, baby. Check it out. Look at that sexy tractor. Looks way better than this stupid thing up here, which look at this. Look at all this carbon dioxide going to the atmosphere. That's bad. I got no smoke coming out of my tractor, so it's way, way better and even more accurate. So, now that we've got my awesome tractor drawn, we have to draw a free body diagram. So I've drawn the X and Y axes going this way, similar to the log, to make our lives a little bit easier, and I've drawn all the applicable dimensions. Now, here's where this statement back here comes into play. We're told that the front wheels are free to roll. So that means that the front wheels, the only thing that they're doing or experiencing is a normal force at B. There's no tractive force. For the wheels in the back, those are drive wheels. So we have normal in the back, but the key difference here, and this is where I'm going to draw our important red arrow, is that we've got force of friction at the back wheels right here. And I'm going to draw this line extra long just because I want to make sure that you can see the force of friction right there. Okay, so now that we've got our force of friction back here on our drive wheels, we've got NA, we've got NB. The other thing that we have to draw is the weight of the tractor acting down. Now, just like we did for our log, we'll break this into its two components so that we've got the component here in the Y direction, and we've got a component in the X direction. Now, there's not much space to write that, so I'll just put the angle here, and we'll be able to come back and solve for those things in the actual equations. So now what we need to do is we also need to include the force that the log is applying onto the tractor. Now, this is Newton's third law. Now, if we look at this free body diagram, the force is pushing on the log from the tractor. The tractor is going to feel the log pushing on it. So we're going to have FLT. And we know that this distance right here is 1.25 feet. Okay, so that's pretty much it. Now what we need to do is I'm going to flip over onto the next page, and I guess I'm going to have to redraw this free body diagram because I should have drawn it on a new sheet, but I'm going to draw it on the next sheet, and we're going to do all the equations we need to solve the rest of the problem and answer the second question, which is essentially, after we figured out how much force is required to move the log, we need to figure out how much force is required to move the tractor and the log together. So let me pause, redraw my sexy tractor on the next page, and we'll finish the problem. Okay, I've redrawn my sexy tractor, and now we're going to answer the second question, which essentially is how much force is required to push the tractor up the hill. And recall from last time, or the last page, we had that the force acting on the tractor from the log is 366.3 pounds. Okay, so we've got our free body diagram over here. Essentially what we need to figure out is, what's this force of friction going on back here? And is this force of friction going to be greater than FLT and all the other X forces pulling down? So let's write our sum of the forces in the X equation. That'll be a good place to start, because ultimately that's the line of action that our tractor is moving on. So our sum of the forces in the X is going to be equal to 0, which is going to be equal to the force of friction acting at point A minus the component of the weight going down the ramp, which is going to be W sine of 10 degrees, minus FLT, the force of the log on the tractor. Now we know this and we know this, but we don't know the force of friction at A. So the force of friction at A is going to be equal to, based off this equation, equal to 8,000, which is the weight of the tractor, right up here. 8,000 times the sine of 10 minus FLT, which is plus 366.3, because we moved both of these things to the other side. When we do that, we get that the force of friction at A is 1,755 pounds. So this is the force necessary, or the force needed to move our tractor up the hill. But this doesn't necessarily mean that our tractor can move up the hill. We have to compare the value we just calculated, essentially force of friction needed. And what we're going to do is we're going to say, how does that force compare? Is it equal to, less than, or greater than the force of friction maximum? Well, we know that the force of friction maximum is equal to mu s times n, which in our particular problem, the only n that's acting is the normal force at A. So we have mu s times NA. So essentially what we need to do right now is we need to solve for NA. Now if we look in this problem, we've got NA is unknown, NB is unknown. So we've got two unknowns in the y equation. So that's not going to be solvable. The only way we can solve this is to sum the moments. And what point are we going to sum our moments about? It's a great question. Well, if we did it at A, NA wouldn't be in our equation. But that's what we're trying to solve for. So we're going to want to do the sum of the moments about point B, which is the bottom of this wheel right over here. If we do that, then we'll have only one unknown, which is NA in our equation. So let's do it. Sum the moments about point B. That's going to get us FLT times 1.25. According to line of action, will be counterclockwise. So we've got FLT times 1.25 counterclockwise. NB doesn't count because that's at point B. We do have two components of the weight, actually. Our one component of the weight, as you can see, it's a little bit off in my drawing, but W cosine 10 is 3 feet away, and that would cause things to go clockwise. So we say minus W cosine 10 times 3 feet. And that's clockwise, so we have that being negative. We also have this component of the weight right here. And realistically, when we're doing this moment equation, we want to draw that component of the weight right there, because that's actually where it's acting. Well, how far is this away from point B? Well, that's what they tell us right here, is this 2.5 value. It's the first time this actually comes into play. So that would cause things to rotate counterclockwise. So we're going to have plus W cosine of 10. Oh, wait, sorry. W sine of 10 times 2.5. And I'm actually just realizing that this W cosine 10 times 3 would actually cause things to rotate counterclockwise about B. My mistake. So this actually should be counterclockwise, positive, just like this is counterclockwise and positive as well. So now we've got these two components, this force. The only thing we're going to have left is NA, because our force of friction is at the bottom of the wheel and will also pass through point B. So we're going to have NA times 10, and that'll be our clockwise force that balances everything out. So then we have minus NA times 10. Now recall we've already solved for FLT. We know our weights, so the only thing we don't know is NA. So we can solve for that. And what we get is that Na is equal to 2,757 pounds. Yeehaw! Okay, now that we know this, we can solve for the force of friction maximum. So the force of friction max is equal to mu s, which is our wheels, 0.8, times Na, which is 2757. So the force of friction maximum is 2,205 pounds. So now we go back to our inequality, our question that we had right here. So FF needed, the force of friction we need to push everything, is equal to a value of 1755. And our FF max is equal to a value of 2205 pounds. So if the force of friction needed is 1755, we can tell that that is less than the force of friction max, which is 2205. Now, because this is the case, because the force we need is less than what friction can actually apply, that means that we're good. We can actually move the log up the ramp before slipping. Had this been the other way, if we had needed, let's say, 1,000,000 pounds of friction, but friction could only apply 2,000 pounds, then we would slip and we wouldn't move. But because the force we need is less than the maximum force that friction can apply, our answer to this problem is essentially we box this and say that our tractor can push the log up the hill. Which, that is a relief, because if not, we would have rented this tractor, presumably, pumped all of these terrible greenhouse gas emissions for no freaking reason. And we were cutting down trees. What a sad problem. But the good news is that we can move it up the hill. And up the hill is a magical paradise full of other trees that this tree will become friends with and become very happy. The end.